Welcome back. This is reading quiz number 7, which is all about difference quotients and how we might use the difference quotient to find derivatives. Well, how do we find these derivatives? We talked about this term earlier in the rate of change, reading quiz number 6, and so we're going to investigate that a little bit more here. The connection between the instantaneous rate of change, or IROC, and the derivative, which is a function that describes the instantaneous rate of change for any possible value, was made in a previous reading. There's one definition, however, that we're going to use more often than others, and that's called the limit of the difference quotient. In this case, we're going to look at the difference quotient of f of x plus h minus f of x over h, which is represented by the diagram over here to the right. In other words, we're finding the slope of the line that connects the points f of x plus h and f of x, the y coordinates. And the reason why we do a limit is so that we can find the instantaneous rate of change. What happens to that average rate of change as our h value gets closer to 0? That's what defines our derivative. And if you can picture this, what's going on is the h is getting smaller, and so the x plus h gets closer to x. And so we have more of a tangent line than we do a secant line. The statement on the left, which is f prime of x, is what's called the derivative of f, and is pronounced, as I just said, f prime of x. This isn't the only notation we'll see. If our function y is equal to f of x, we can also say f prime of x is equal to dy dx. It's also equal to y prime. We can also say that's the derivative of f with respect to x, which is the df dx notation, or we can just say the derivative with respect to x of f of x, and we'll expand on more of these later. So an example from the reading, how do we actually find these derivatives? Well, we plug our function into the difference quotient and we simplify. For example, find the derivative of f of x is equal to x cubed minus x. Remember the definition, f prime of x is equal to limit as h goes to 0 of f of x plus h minus f of x over h. We plug in the actual function, which is x cubed minus x. So we're plugging in x plus h in for x cubed and x plus h in for x. When we do that, we can simplify. We expand and simplify. We get limit as h goes to 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed minus x in parentheses. It's important to make sure that you keep your parentheses because otherwise you might lose a negative. A hint on these is you should always be able to cancel out an h at the next step. So anything without an h should be canceled out, as we can see. Look at what we're left with. Limit as h goes to 0 of 3x squared h plus 3xh squared plus h cubed minus h, all over h, and we can factor out that h and cancel. So we're left with limit as h goes to 0 of 3x squared plus 3xh plus h squared minus 1. Now, we've canceled out the part of this quotient that would make our numerator and denominator equal to 0. Once we've canceled that out, we can plug in h is equal to 0, and we get 3x squared minus 1, which is what's called our derivative. It's a function that describes the instantaneous rate of change at any point x. This allows us to find the derivative of the slope at any x value. For example, at x is equal to 2. All we do is plug in our 2 into our derivative equation. We get 3 times 2 squared minus 1, which is 11, which says our slope at x is equal to 2 is 11. Find the derivative of f of x is equal to square root of x. So, as before, we plug square root of x in for our f of x, and we find that f prime of x equals limit as h goes to 0 of square root of x plus h minus square root of x all over h. It's not easily factorable, so what we do is we multiply and divide by the conjugate, which in this case is square root of x plus h plus square root of x. When we multiply the numerator, we notice that we get a square root of x plus h squared minus square root of x squared, which cancels down to just an h. I left the denominator alone so that we can see that all we need to do is cancel out our h on our top and the bottom. We're left with limit as h goes to 0 of 1 over square root of x plus h plus square root of x. Plugging in h is equal to 0, since we factored out the part that gave us a problem, we're left with 1 over 2 squared of x. This is a derivative that we need to know. We'll be seeing this one quite frequently. Example 4 from the reading. For the following problems, the following limits represent f prime of a for some function f and some number a. Identify the original function and a in each case. So in our example here, we have the limit as h goes to 0 of square root of 9 plus h minus 3 all over h. Somehow that needs to match up with our function f of x plus h and our other function f of x. So what we do is we notice that the function appears to be a square root function. Because we've plugged in a 9 plus h into the square root of function, the h matches perfectly, and our x must be equal to 9 because we've got the square root of 9 equal to that 3, that extra part we got here. So in other words, our f of x, our function, is square root of x. Notice how the 9 plus h has been the input for the function. And then take that back, the value of a should be 9, not 3. Seeing if you're paying attention. Question number 75 from our guided practice. How do we apply derivatives? What do they mean in real life? So let g of t be the height in inches of Rebecca, t years after her birth. What are the units of g prime of t? And then what can you say about the signs of g prime of 10 and g prime of 30? Well, the derivative has everything to do with cats because the derivative involves per, just like a cat's purr. So the units of the derivative will be the units of our dependent variable over the units of our independent variable. In this case, our dependent variable is the height of Rebecca, and our independent variable is the number of years after her birth. So the derivative will be measured in inches for our dependent variable per year, which is our independent variable. G prime of 10 is positive, and we can guess that Rebecca is growing, and so her height is changing in a positive way every year at the time t equal to 10. But G prime of 30 is probably close to 0 because she stopped growing. So you need to start imagining these as rates of change, inches per year. Is she growing? If she's growing and her inches per year is positive, then that means the derivative is positive. If the number of inches that she changes per year is steady, then that means that g prime of 30 is close to 0.